I don't know, maybe we worked on this one already. Y prime minus 2y equals e to the 2x. And this has an initial condition of y of 0 equals 2. Now, I don't think we actually worked on this one. So p of x is equal to minus 2. G of x is equal to e to the 2x. Mu of x equals e to the minus 2 equals e to the minus 2x. So y equals e to the 2x, e to the minus 2x times e to the 2x dx plus c e to the 2x. And this makes the integration easy. E to the 2x, and that's e to the 0. So that's dx plus c e to the 2x. We have x e to the 2x plus c e to the 2x. And we say y of 0 equals 2 equals 0 plus c. So c equals 2, and y of x is equal to x e to the 2x plus 2e to the 2x, and we can factor that out, and we got e to the 2x times x plus 2, and that's y of x. And that's our solution. Boy, a lot quicker than the previous problem. And that's supposedly a more advanced problem. I don't get it. All right, so we are given, let's see, are there any more problems that we can solve? All right, why don't we look at this one? This is given as an example in the book. All right, we got x y prime plus 2y equals 4x squared. And I don't think we have any initial conditions given with this. So we have y prime plus 2 on x, y equals 4x. And so p of x equals 2 on x, g of x equals 4x, and mu of x is equal to e to the 2 dx, that's equal to e to the ln x squared is equal to x squared. So y equals 1 on x squared. Okay, x squared times 4x dx plus c on x squared. And this is 1 on x squared, times, now this is going to be, whoops, why did I do that? Times 4x to the third dx plus c on x squared is equal 1 on x squared times 4 on 4x to the fourth plus c on x squared. That is x squared plus c on x squared. And basically that's the solution. And what they, let's see, condition. Oh, they did give an initial condition. The initial condition was y 1 is equal to 2. So we have y 1 equals 2 equals 1 plus c. So c equals 1. And then we have y of x equals x squared plus 1 on x squared. And that's our solution for this initial condition. But if c is arbitrary, if there was no particular, if we left it in general form, we would have a family of curves for different values of c. And so we can have a parabola of c is 0. We can plot these different curves if we chose different values of c, and these things that look like that for different values of c for this function. And it's easy to plot. You can do something like that in Excel and see the different curves that come out of this for different values of c. And I'm looking for a, they were saying if you change the initial condition to let's say y of 1 equals 1, so we have 1 equals 1 plus c, so c equals 0, and then y of x equals x squared. So that's one of the curves we saw. That's the parabola. And we can, it's interesting to take a look at the different possibilities and plot this curve for different values of c. And that's true for any of these differential equations because there's an infinite number of solutions given different values of c. So that's something that you can do for yourself. I'm not, as you know, a very good graphic artist, so I'm not going to attempt it. Let's take a look at some of the problems they got here. See if there's anything of interest here that may. We got y prime plus 1 on x, y equals sine of x for x is greater than 0, and these don't have any initial conditions. All right, so p of x, 1 on x, g of x is sine x, mu of x is equal to e to the 1 on s ds equals e to the ln x, that's equal to x. So then we have y equals 1 on x times x sine x, we've already looked at that one, plus c on x. And we use integration by parts, so u equals x, du equals dx, and v equals, let's go with cosine x, and dv equals minus sine x dx. All right, so here we go. We got y equals 1 on x. Well, before we do that, my mind is drifting. I was just thinking about a wedding that occurred yesterday. So we have x, cos x. Oh, darn, I hate this. Why does it shift so easily? Cosine of x is equal to u minus x sine x dx plus cos x dx, and we have x cos x minus sine x equals minus x sine x dx. And now with the negative sign, we got sine of x minus x cos x equals x sine x dx. And that goes into the integrand, so we have y equals 1 on x sine x minus x cosine of x plus c on x. Now that's the general solution for that particular problem. And it will generate a family of curves. Let's see, I just want to check on the, this is section 2.2. Alrighty. Alright, let's see, I think what they did was this, they went one more step. So they went one on x times sine of x plus c minus cosine of x. That's the result that they gave. So it's not really that much of a matter. It's a little simpler form. So it's these are the different solutions, and it's a family of curves. So if you plot this, it all depends on what value of c. So you're going to get different curves, an infinite number, that is. To be quite honest, that was a problem that they gave earlier. I don't know why they would have given that same problem. Here's one I think is new. X squared y prime plus 3xy equals sine of x on x. Okay, so this one is different. Again, it's a general solution we're looking for, so it's going to be a family of curves. We have p of x equals, all right, so let's do one thing first. Let's get this 3 on x, y equals sine of x on x to the third. I see where this is going. So p of x is 3 on x. G of x is sine of x on x to the third. Mu of x, if you haven't got it now, it's already, you can see it is going to be x to the third. And the reason for that is mu of x is equal to the exponent of 3, 1 on x dx, and that's equal to e to the ln x to the third and x to the third. So now we use our theorem. Oh boy, my allergies are starting, something's hitting me now. Okay, so x to the third sine x over x to the third dx plus c on x to the third. And we see those cancel out. y equals cos of x, dy equals minus sine x dx, y equals minus sine x dx, and that's cosine of x equals minus sine x dx. So this is 1 on x to the third times minus cosine of x plus c on x to the third, so y of x equals 1 on x to the third times c minus cosine of x, and that's our general solution. And let's just check in the back. Yep, that's the exact form, how they got it. Now you got to remember, these problems are carefully crafted to be solvable. The vast majority of differential equations are just not going to be solvable. These ones were particularly chosen because they can be solved. So here's one that looks interesting. Plus tangent x of y equals x sine of 2x, and they give the interval, they say, between negative pi on 2, so this is only true for that condition. And if you remember y, if you plot tan of x, at pi on 2, you get sine of x over cosine of x, and that cos, you end up with something like this. And you can't have division by 0, so you're bounded by pi on 2 you're bounded asymptotically by pi on 2, and I think it's let's say pi on 4 is 1, so this is pi on 2 minus pi on 2, and pi on 4 is half of that, and that would be 1, and that would be minus 1, I think. Let's see, that's, yep. And I think the curve, it looks like this for a tangent function. They go asymptotically. So this is tan of theta. So that's why we have the interval. That's why that condition is, if it's integratable or continuous on the interval given. This is not, if the interval was different, let's say between x pi and 0, then that wouldn't work. We couldn't use that interval So that's why that condition is important. That's why they give it. Okay, so now we have an interesting problem here, because we got p of x is equal to tangent of x. G of x is equal to x sine of 2x, but sine of 2x, sine of 2x equals 2 sine x cos x. So that's something that may come into play. So let's write that out. G of x could be 2x sine x cosine x. That's equal. And let's see, mu of x is equal to e to the tangent x dx. All right, so we have, it's been a while since I've integrated the tangent of x, so basically we have cosine of x to the -1 times sine x dx. Let's say u was cos x, du would be equal to minus sine x dx. So we have u to the -1 minus du, and that is equal to minus du equals minus ln of u. So we have an interesting problem here. So this is equal to minus ln of cos x, and so this is equal to e to the minus cos, whoops, I'm sorry, that's not exactly true, minus ln of cos x, and let's erase this, and this is equal to e to the ln of 1 on cos x, and that's equal to 1 on cos x, which is the secant of x. All right. So y of x is equal to 1 over secant, so that's cos of x. Now here, mu x, we got cosine x. Okay, so we got x sine x. Okay, let's take this slowly. I don't want to make mistakes. All right, so we have x sine. Okay, just a minute. I want to make sure I got this correct. Okay, so we have x sine of 2x. So we have x sine of 2x times secant x. Let's see, mu of x is secant of x, which is cosine of x dx plus c cos of x. All right, now remember our identity, double angle formula, cosine of x times 2 x sine x cos x on cos x dx plus c cos x. Now these cancel, and we're back to x sine x. Okay, so we're back to the UV thing again. And what was that? If we choose x u equals x, du equals dx, and v equals cos x, dv equals minus sine x dx. And let's see, there was a negative sign in here somewhere, wasn't there? Oh, well, that was taken care of by this. Okay, so we're back to this cos sine x minus x cos x is equal to x sine x dx. So we put that in there, y of x equals cosine of x times sine of x. There's a 2 in there, so let's not forget that. Minus x cos of x plus c cosine of x. And that pretty much does it for us. I mean, we could multiply through. Actually here, we got something here. We got an identity, so we have sine of 2x minus x. Whoops, let's get that right. 2x cosine squared x plus c times cosine of x. And that should be the answer. Let's, again, it's a general solution, family of curves. Let's take a look at that one, number 3. Yeah, well, that's the answer. They didn't carry it out exactly the way I did. They didn't use the identity. I did. I guess maybe because it didn't really make it simpler. But their answer is equivalent to mine. Basically what they've got is this, and you can see that it matches. So that's what they've got. I'm not quite sure that their form is necessarily superior to mine. I guess it's smaller in terms of its order. I mean, in the sense that I've got a cosine squared in my answer, but basically that's the only thing. Yeah, this is correct. Yep, everything is the same. And I made use of the double angle formula. And that's it. I would have thought that's how they would have given it myself, but okay. Let's give another one a try. That was an interesting one. Again, you got to remember that these problems are arranged. Plus 2y equals e to the x. Simplify it a little bit. All right, so p of x we have g of x and mu of x Okay, so again, these problems are specially chosen and worked on so that they have a solution. So y is equal to 1 on x squared. Mu of x is x squared e to the x on x dx plus c on x squared. So here we go. This is equal to 1 on x squared. We have x e to the x dx plus c on x squared. So again, we got the u dv, so we got u equals x, du is dx, v equals e to the x, dv equals e to the x dx. So now we got x e to the x equals x e to the x dx plus e to the x dx. So we have x e to the x minus e to the x equals x e to the x dx. Now we've plugged that into the integral. And we got y of x equals 1 on x squared times x e to the x minus e to the x plus c on x squared. We can factor. We can bring this out. We can go I don't know if that's any simpler. Let's do it this way. E to the x on x squared times x minus 1 plus c on x squared. So that's y of x. And checking our solutions. Yeah, that's our solution. This is correct. And now let's see what they are throwing at us. Mr. Boyce and DePrima. Yeah, we got initial value functions. So here we go. We got x, y prime plus 2, y equals, oh, we got a nice polynomial here, x squared minus x plus 1. Is that a square? Let's try that. What is x minus 1 times x plus 1? X squared minus 1. Let's not do that. How about this? I don't think that's a, you know what? I don't think that's a square anywhere. That doesn't work. I don't think we have a squared situation there. Let's just leave it. So let's get rid of this spot. All right, so we got to divide through. We got y prime plus 2 on x, y equals x minus 1 plus 1 on x. Okay, so p of x is 2 on x. G of x equals x minus 1 plus 1 on x. Mu of x is x squared. And we've done enough of these to show that. And so we end up with, using our theorem, okay, x squared times x minus 1 plus 1 on x dx plus c on x squared. And this 1 on x squared, and this is times the integral of x to the third minus x squared plus x dx plus c on x squared. So now this is just a simple integration. Plus c on x squared. This is an initial value problem, okay? They did give y of 1 equals 1/2. So we're going to have to solve for that to get an explicit solution for c. So let's simplify this a little more. We got 1 quarter x squared minus 1/3 x plus 1/2 plus c on x squared. That's y of x in the general, and y of 1 equals 1/2 equals 1/4 times 1/4 minus 1/3 times 1/2 plus 1/2 plus 4c. And so this is interesting. We got 1/2 equals 1/16 minus 1/6 plus 1/2 plus 4c. So now we have to find a common denominator. All right, so let's see. What's 16 times 2? 1232. That doesn't work. 16 times 3, that should be 48. 48 should work. 6 times 8 is 48, and 22 times 24 is 48. So we have 1/2 equals, all right, 3/48 minus 8/48 plus 24/48 plus 4c. And now we can do 24 minus 8 that's 16 plus 3, 19. So we have 1/2 minus 19/48 equals 4c and 48. So that's 24 minus 19. So that's okay. 3. 5. What am I doing? 5. Okay, 24 minus 19 is 5. So we have 5/48. Oops. 48 times divided by 4 equals C. Oh, God. 48, 4 is 32, 16, 19. So we got what? 5 192s. Something doesn't seem right. Did I screw up my math? Let's see. 1, right? 1. What did I do? Oh, I'm an idiot. My brain is just not working today. Okay, we got this freaking solution, general solution. So we got 1/2. Y of 1 equals 1/2 equals 1/4 minus 1/3 plus 1/2 plus C. I don't know what I was doing. So the common denominator is 12. So we have 1/2 equals 3/12 minus 4/12 plus 6/12 plus C. All right. So we have 5/12 plus C. Okay, that's 6/12 minus 5/12 equals C equals 1/12. All right, that's better. And so Y is this. Oh, God, that was awful. Sorry about that. There we go. That's the solution right there, the explicit solution. And we really screwed up the math. I was I was putting 1/2 in for the variables, and it was 1. It was Y of 1 equals 1/2. And you see, you got to pay attention. And the last two problems, I've shown how not having your mind focused on it can give you very quickly give you an erroneous answer. So this one, number 5, yep, the number is the 12th. All right. Huh. What did I screw up? No, their answer is wrong. When you integrate x to the third, when you integrate x to the third dx, that's 1/4 x to the fourth, because if you take the derivative, dx of 1/4 x to the fourth, it's equal to x to the third. So they are incorrect. Oh, no, they're not. They are not. Okay. Boy, I tell you, if they are incorrect, that would have been... You know, it's funny, I did find an error in a book once, and I contacted the author, and they were thankful. Yeah, so what they did was this. They made this all 12. So this is 3x squared minus 4x plus 6 on, whoops, plus x squared, 1 on x squared, all on 12. And that's what they did. Yep. That's it. That's their solution. And nothing was wrong. And we did this correctly, except for my horrendous math. When I was evaluating, I plugged in. You see, these are the kind of mistakes that you can make if you're nervous, you're taking a test, and you're not thinking, so you got to pay attention. In the case of what I just did was I saw the initial condition, and then I plugged in the answer for the variable. So I did x squared was 1/4, x was 1/3 times 1/2, and so I had 1/4 and 1/6 and 1/2, and I tried to find common denominators for those, and that really screwed me up because I was looking for something totally erroneous. And you just have to pay attention, and I wasn't paying attention there. I let my mind wander. So maybe there's some lesson there, but you can rest assured this is indeed the answer. This everything under this block is the answer to the explicit condition y of 1 equals 1/2. Okay, so now let's try another one. I don't know if I should be trying. I'm not paying attention very well here. Plus, I only got about 2 hours sleep last night, which doesn't help matters any, does it? Okay, so we have another one. X to the y prime plus y equals e to the x, where y of 1 equals 1. Let's not try and make a mistake this time. So divide through by x, and RP of x is 1 on x, g of x equals e to the x on x, mu of x is equal to x. Okay, so we got all our necessary elements, factors to our problem, to solve our problem. We got 1 on x, e to the x on x dx plus c on x. This is going to be pretty simple. Whoops. I don't know why I did that. And now, that's our general solution. And we're given y of 1 equals 1. So we have 1 equals 1 over 1 e to the 1 plus c over 1. 1 equals e plus c. 1 minus e equals c. So, therefore, we have y to the x is equal to e to the x on x plus 1. Let's see, 1 minus e on x equals 1 on x times e to the x minus e plus 1. But e is .718. Something is a little weird. Is that the right? Yeah. And we did this correctly. Yeah. We didn't do anything wrong. So, e to the 1. Yeah, okay. Well, let's see what they got, if they have anything in the back. Okay, that was problem number... Yeah, that's it. That's the solution. Right on the money. Okay, we got it right. So this is it. And my 4 hours of sleep, that's another thing. It's probably not the best idea to try to do this kind of stuff when your eyes are heavy. All right, that was a relatively quick and simple problem. See if there's something else we can do. Wow, this one looks challenging. Y plus cotangent x y equals 2 cosecant x, and I guess we're given y of pi on 2 equals 1. Okay, so this is going to be an interesting situation. Cotangent is cosine over sine. So let's say p of x. Let's get rid of these hand lines. Okay, so p of x is the cotangent of x. G of x is equal to 2 cosecant of x. Mu of x is equal to the cotangent of x dx. Now, cotangent is sine of x, -1, times cosine of x. So let's say u equals sine of x, du equals cosine of x dx. So we have 1 on u du. So we have e to the ln u, so that's u of x, equals u equals sine of x. That's our mu of x. So let's take a look at the solution. Y equals 1 over sine, so that's cosecant of x. And we have sine of x times cos of x over sine of x. What am I doing? This is why you got to be careful. All right, sine of x, that's our mu of x. G of x was cosecant, so we have 2 times 2 on sine of x dx plus c cosecant x. These cancel, and we have cosine of, damn, so used to working with certain trigonometric functions. Cosecant x times 2 dx plus c cosecant x. And so this is 2x cosecant x plus c cosecant x. That's the general solution. So y of pi on 2 is 1. And so we have 2 pi on 2 times cosecant of x. So that's 1 on sine of x, but pi on 2, sine of pi on 2 is 1, so that's 1 plus c times 1. And these cancel, and so we have 1 minus pi equals c. Then that gives us the answer. Y of x is equal to 2x cosecant x plus 1 minus pi cosecant x. And now we can do a little grouping. We got y of x equals 2x plus 1 minus pi cosecant x. That should be the solution for that. So let's turn to the page and see if I screwed up in any way. Yeah, that's it. 2x plus 1 minus pi. Yeah. The answer they put is this. They put it back into familiar form using sine instead of the cosecant. So they're both correct, and we can move on. I like solving as many problems as I can, and the reason I think it's beneficial is that going through the problem, is beneficial to go step by step. That way you can see the process right from beginning to end. And here we're given y of pi is equal to 1 on pi. All right. So first off, we got to divide through by x. And we have p of x is 2 on x. G of x is equal to sine of x on x. Mu of x, if you don't gather by now, is x squared. E to the 1 on x dx. That's equal to e to the ln x squared equals x squared. Okay, so we have y equals 1 on x squared. And we have x squared sine x on x dx plus c on x squared. And we're back to this. So we're back to this x sine x integral. Use the u equals x du equals dx. V equals cosine x dv equals minus sine x dx. So we get our usual. We got our x cos x equals minus x sine x dx plus cosine dx equals minus.
Hey, Grandpa?
Yeah.
What was the song Woody Guthrie wrote about Trump's father?
It's called Old Man Trump.
It was called Old Man Trump?
Yeah. So now we have x cos x minus sine x minus sine x dx, and then that reverses all right, so now we plug in to our integral. We got y equals x squared sine x minus x cosine of x plus c on x squared. But then we have y of pi equals 1 on pi. So we have now 1 on pi equals 1 on pi squared times 0 minus pi times -1 plus c on pi squared. And we got pi equals, alrighty, 1 pi plus c on pi squared. So we have pi equals pi plus c, c equals 0. So our solution then, c is 0. So our solution is simply, when we plug in the conditions, we got y of x equals sine x minus x cos x x squared. And let's just check on that answer. Yep, that's it. So we have the correct result. Despite Woody Guthrie having written a song, it wasn't Arlo. Hey, Steph? It wasn't Arlo Guthrie.
I didn't say Arlo, I said Woody.
Oh, okay. That's right.
They had his land is our, this land is our, your land, this land is my land.
Right.
And I told Felix that was written by Woody Guthrie.
Woody Guthrie, right. All right. Well, let's see. How many more of these? They really don't give too many problems, do they? Okay, let's see. That was number 8. Here we go. Sketch several members of the families of integrals. Okay, so in this problem, they want you to sketch the different families. Probably would be best would be to use Excel, and we can solve these. We can solve these and then plot them. So let's give these a try. So here we got p of x 2 on x, g of x equals 1 on x squared, but mu of x is equal to that's x squared, so y equals 1 on x squared times dx plus c on x squared, and that's equal to 1 on x plus c on x squared. For I think these are x greater than 0. That's what they want us. Continuous at, let's see, discontinuous. Each of the equations, problem 9 through 12, has at least one discontinuous coefficient at x equals 0. At x was, and solve each equation for x greater than 0 and describe the behavior as x goes to 0. All right, so we'll need to, I think we'll be best served by using Excel. So we can take a look at each one. So we've got, we'll record these. We have y prime equals 1 on x plus c on x squared. X equals 0 and x. All right. Okay. I just want to make sure that I got this right. Yeah, that's the solution. And they want the limit of y as x goes to 0 is equal to infinity for all c. And that's basically, so that solution, limit of y goes to infinity as x goes to 0. All right, just make sure that when we go to Excel, I have the right thing. Let's look at the next problem. Y prime minus 1 on x, y equals x. That's the next problem. So let's separate these. Okay. And here the limit as x goes to 0 of y goes to infinity, actually, not equals. That makes sense because we have 1 over x, and as x gets very small, 1 over x gets very big. And 1 over x squared gets even bigger faster. So in both cases, we're going to be going to infinity. All right, so let's solve the next one. P of x is equal to minus 1 on x. G of x is x. Mu of x equals e to the minus 1 on x dx equals e to the ln of 1 on x, 1 on x. So y equals x times 1 on x, x dx plus c x. And here we have x dx plus c x, and that's equal to x squared plus cx. And they want us to look at now, how is that discontinuous at x0? I don't see. Did I get this solution right? Yeah. Yeah. So they want the limit as x goes to 0 of y, which is 0. It's kind of silly, but yeah, that's it. And they want us to plot this. It's going to be a parabola. So we'll keep that one in mind. So we'll plot those two. So here's the second one. Y is equal to x squared plus cx. We got a family of curves there. And every one is going to go through 0. Now, the next problem we have let's see, the next problem is y prime minus 1 on x, y equals x to the half. All right, so that's interesting. So here we go. P of x equals minus 1 on x. G of x equals square root of x, and mu of x equals e to the ln of 1 on x, 1 on x. So y is equal to x, 1 on x, x to the 1/2 dx plus c on x. Nope. Screwed that one up. C times x. All right, so we got a little commotion going on upstairs. That's why I'm a bit distracted. All right. So this is what am I doing there? I don't want that. I want that. Okay, so this is equal to 2 x to the 3/2 plus c x. And they want us to plot that one. This one's we have to remember that x has to be greater than 0. The limit is y okay. So we will take a look at that behavior. And this one, I would just want to check and make sure. I got the is number 11. Yeah, that's the answer. So this is correct, and we're gonna plot that one and see a family of curves for that and their behavior, and when x is 0. We know that it can't be less than 0 because then you have the square root of a negative number, and then you're talking about complex numbers. Okay, so we got 1, 2, 3. We have a little guy having a meltdown up there. That's a problem with this COVID crisis. We have to have remote kindergarten in our house upstairs. All right, interesting. Okay. All right. Just checking emails there. Okay, so this is the last problem that they give in this section, y prime plus 1 on x, y equals cosine of x on x. You can already see this one, where we have p of x is 1 on x, g of x equals cosine of x on x, and mu of x is going to be x. All right. Now, our solution is 1 on x, x cos x on x dx plus c on x. And this is simply x cos x plus c on x. And that is 1 on x sine of x plus c on x. And again, we got to look at what happens with y as x goes to 0. We'll plot out the curves, because it's a family of curves. Yep, that's the solution. And we're going to take a look at this we're going to take a look at this and see what the different curves look like. And I think this was the last problem. So they gave us 4 to plot. And so we're going to take a look at c plus 1 on x sine, let's see, that's not the curve. I don't know what I'm writing. Okay. 1 on x sine x plus c on x. All right, so we got a number of curves, and now we are going to use Excel, and we'll take a look at how these curves plot. I thought we'd end the video with an exercise in Excel to show how we can plot the curves. There were 4 equations where the problem asked us to plot the curves for each of the solutions, the family of curves. But before that, I want to talk about, and actually we use this in 2 problems. Talk about a problem that we solved earlier, and that was with the e to the minus x squared. That's the Gaussian. And you can see here, this is the general form for the exponential function known as the Gaussian. Y equals a to the e raised to the x minus b squared divided by 2c squared. And that is the general form of a bell curve. And we'll take a look at that in a minute. This is an example of the Gaussian curve. And we'll talk about that a little more. Where in this formula, A is the amplitude or the height of the curve itself. C is the standard deviation. And in the case of the particular case that we looked at, C, or the standard deviation, was 1 over the square root of 2. And but in most cases where you use the Gaussian to model statistical data, the standard deviation is going to be whatever comes out of the data set. And that C, or standard deviation, is actually, I should write that in there because that's the standard deviation, really. And this is a particular case of the standard deviation. So this is the standard deviation. And then B is the center of the apex of the curve. As you know the Gaussian curve, you have the apex right there. Well, you can shift that along the x-axis. The center of that distribution is determined by the factor b. And in our particular case that we solved the solution to the differential equation that we had, we were looking at e to the minus x squared. And that is the special case where A is 1, C is 1 over the square root of 2, because the denominator here is 1. And in order to achieve 1 with C, you have to have 1 over the square root of 2. So that's 0.707 for this particular form of the Gaussian curve, and B equals 0, so it's centered on x equals 0. And we discussed at least the strategy of how to obtain the equivalent of the Gaussian curve in a polynomial function, an infinite series. This is a Taylor series. And in the problem, we at least hinted at gave the strategy of how to obtain this particular curve, this particular Gaussian. In the model that we're going to be looking at, I carried it out to 171 terms. So we'll take a look at that in a minute, and we'll show how precise, how very accurately this polynomial, this Taylor series, mimics or describes the actual curve itself. And the integral, now, this is an interesting part because the integral of e to the minus x squared, or the integral of the Gaussian, can only be solved over the infinite domain when x is minus infinity to plus infinity. That's the entire domain of the curve. And there is a special trick to solving this integral. It's actually, you break it up into two integrals of the same, where you have e to the minus x squared and you have multiplied by the integral of e to the y squared, and so you have x squared plus y squared, and you can use polar coordinates, solve that integral, and then take the square root. And what you end up with when you solve this integral, you end up with the square root of pi. Pi being 3.141592, and so on. It's an infinite decimal points, and the square root of pi is approximately 1.77245. You can carry it out how many different places that you want. It's another never repeating, never ending decimal places. But this will give you enough precision for whatever problems you're solving. And the interesting thing is that when you integrate this series, you can integrate it. You can use this to substitute into this integrand. And when you use the Taylor series in the integrand, you end up with this series right here, this Taylor series. So this is the integrated form of the Taylor series of the Gaussian. So that's the interesting thing, is that this gives you the integral, and it's interesting. It's just like taking the integral of a polynomial, or x squared, and you increase the order of the variable by the power of 1. So we end up with the exponent 2n being 2n plus 1, and you divide that variable by 2n plus 1. So you have now a Taylor series whose denominator increases even faster than the denominator of the factorial, because you have 2 to the n plus 1 times n factorial. So this series converges even faster. In fact, the denominators, you end up with, well, we'll show you with the table that I made with the model, this Taylor series model of the integral, and it works out surprisingly well. You'd be pretty surprised at the accuracy. Now, here I have two plots, as you can see here, the blue one and the orange one. And the blue plot is the model. That is the infinite series that we just saw right here, this integration of the Taylor series right here, this infinite series that resulted from integrating. That's what we have right here. Actually, I'm gonna let's see, right here. This is it right there. I'm going to highlight that one, because that's the integral of, you can see the little formula there. Here, I actually, this is the model, this table here, or sets of columns here, give the model for the, it's a Taylor series model for the e to the x. squared, e to the minus x squared. And that's this blue curve right here. And you can see now, basically, the orange curve is e to the minus x squared, the actual function itself. And I wanted a comparison, and as you can see, these things are almost exact. Now, the only thing difference is about these two, I offset their axes in such a way that the zero for the orange curve is down here at minus 0.2 on the x-axis of the model. This way, the two curves stand out. If I put them on exactly the same scale, that if it wasn't offset, they'd cover each other. So you wouldn't. All you'd see is the orange. It would mask out the blue. That's how close these curves are. The error that you get in the model is very, very, very small, until you carry it out to beyond x equals minus 5.5 to 5.5. When we calculated this curve using the Taylor series, once I got to x equals minus 6 to 6, the range of x is minus 6 to 6, the precision or the accuracy of the model fell off. And the reason for that is because I only carried this out to 170 terms. So I carried out the Taylor series 171 terms. In order to expand the accuracy on the x-axis, you have to add more terms. The problem is because of the very, very, very small numbers, the n factorial, 1 over n factorial brings. Here you've got n factorial, where n factorial I think is 170 factorial. You have 1.5 to the minus 10 to the 100 minus 196 power. That's very, very small, and so you need many, 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 many terms to actually expand the x-axis range in which the model is an accurate description. The only thing here is that you really don't need to carry that model out too far, because remember, the area under the curve from negative infinity to plus infinity for the Gaussian is the square root of pi, which is 1.77. And in our situation where b is 0, c is 1 over the square root of 2, and a is 1, the standard deviation for the curve is 1 over the square root of 2. And I show that here in the table. That's one standard deviation. When you have 3 standard deviations, that would be equal to 3 times the square root of, let's see, the square root of 2. So one standard deviation, okay, 1 st dev is equal to 1 over 2 to the 0.5, and that's 0.707. 2 standard deviations, st dev, is 2 times that, so equals 2 times 0.707, and that is 1.414. And then 3 standard deviations is equal to 3 times 0.707, and that's 2.12. Now, when x is minus 2.12 to positive 2.12, you can see that that would bring us somewhere around here, somewhere like that. That's that much of the x range in the curve, under the curve. And when you have that value, 2.121333, you have 99.7% of the area under the curve. And when you have 2 standard deviations, you have 95%. And that is pretty cool, 95.5%. And 1 standard deviation would be 1 times that. That is 68 point. I think in reality, 1 standard deviation gives you 68.4. That's what you would see. So you can see the model isn't absolutely perfect, but it is pretty darn close. And the other great thing about the model, using the integral of the Taylor series, is that you can integrate between 2 x values. Let's say x equals 0.5 to x equals 1.5. Well, that would be on the curve somewhere. Okay, I put the x-axis up here to make it easier to see. So 0.5 would be somewhere here, so that would be the area under the curve between here and 1.5 and there. And so you can get the probability of the area, which is something that you can't get from doing the integral explicitly. So the great thing about using Taylor series is that you can overcome the fact that you can't integrate the Gaussian explicitly or directly. But again, you have to remember there are certain limitations that apply. So if we want the probability of between two points, let's say 0.5, okay, that gives us 0.46. Okay, so that's the value there, 0.46128. That's how many degrees of precision. And B, the upper end of our limit was 1.5. And so that turns out to be 0.85619, and then we just take the difference. Okay, the difference is equal this minus that. That's how we would integrate. And then when you divided that by the entire area, you get the probability. So we have this divided by 1.77, which is the square root of pi, and multiplied by 100, and we end up with a probability of 22%. So you can see how the model now works for you. 22.28%. And that couldn't be obtained if you tried to tried to integrate between 0.5 and 1.5, e to the x between those two limits of integration. So the model really has a lot of utility. They didn't carry the problem out that far. They left the problem unsolved in the book, in the text. They just gave the problem, and then they left the solution as an integral. And so I went further and solved the integral to come up with a solution with an infinite Taylor series for that particular problem. And the thing is about the book, Boyce and DePrima, Elementary Differential Equations, the book that we're using, it gives us these types of techniques that we can use for intractable or unsolvable integrals. And so they go a little bit into numerical solutions, which utilize computers. The fact that you can program Excel in BASIC allows you to use certain numerical methods. Also, they give you some Taylor series solutions, and I'm sure this was one of them. So I kind of jumped ahead of the book quite a bit, actually. But I hated to see the answer just left alone without a solution. I wanted to show that there was a solution. This table over here is an integral, and you can use numerical methods of integration. Here I used rectangular approximations where I divide up the curve. I have y equals x squared, and I also have the Gaussian e to the minus x squared, and I used rectangles that were 0.01 in base width, and then taking the midpoint between 0 and 0.01 as for the height of y to the x squared. So that's the point that I used for finding the height of the curve. That's the height or the length of our rectangle. So we have the height and the base, and so we sum up all of the rectangles between any point A and B, and we have an approximation of the area under the curve for the function. And we can do the same thing for the numerical limit of e to the x squared. And just to show you, we had 22.8% using my model with the Taylor series. If I go to 0.5 right here in the model, and that would be here, and 1.5, and add up, let's see, where's 1.5? 1.5 there, and I'm gonna now sum up all of those. Oh, you know what? It's that's the model for e to the minus x squared. So I'm gonna I went a little bit too far. There we go. Okay, so I added up between x equals 0.5 and 1.5, and that's the area under the curve right there. And if I divide that by the square root of pi, I should end up with, actually, if I carry this out, I'm going to carry it out a few more decimal places. Number, 2 decimal places, that's good. And, well, let's see, that's, well, I should multiply it by 100 to get the percent, times 100. And I got 22.72%. And remember up here with my model, we got 22.28%. So there's a slight difference, but not much. And it's probably because I used probably a broader base on the rectangles. It's not as precise. If I used, let's say, 0.001 for the base and 0.0005 for calculating the height of the rectangle, I would have gotten a more accurate representation of the area under the curve. But you can see what I'm saying. There are two methods that we can get the area under the curve. We could use an infinite series, the Taylor series, which I carried out for 170 terms, or I could use a numerical method for calculating the area under the curve of the Gaussian e to the minus x squared. So you could see that there were similarities there with the answer being. Let's cut and paste it up here so that we can do a little comparison. So you see here how close we've got the solution. Whoops, I'm gonna undo what I just did. I don't know what I did there. I screwed it up. I don't know what happened. Well, I really messed things up. But you saw that I had 22.72 and 22.28. Cancel. So I had 22.28 and 22.72, or 27. I'm sorry, 27, and they're not off at all, really. I mean, that's pretty close. And again, like I said, it was probably I could get a much better estimate by taking the base of the rectangle to be much smaller along the x-axis. So here I've used Excel for both the Taylor series solution to the integral and for a numerical method using rectangles to solve the area under the curve. And they both give very, very good results. And so I just wanted to show you that there are different methods for achieving the same thing. Even if you can't solve a particular integral explicitly. Now, this is the curve that this is a blow up of the curve that we saw before. And the blue curve is our model. The orange curve is our function, and somehow these lines got a little thrown off, but there we go. And I probably right there, and you can see now the only thing, they're actually scaled on the same scale. It's just that I offset the scales by 0.2. So 0 on the orange curve is, which is the function itself, e to the minus x squared when you plot it, is at minus 0.2 on the curve, on the scale for the model curve. Now you may be asking, what happened to the model? Because all of a sudden it's going off. It has deviated after 5.5 on the x-axis. So when you look at the range between minus 5.5 to 5.5, the curves are almost exactly the same. But then suddenly it deviates drastically when you expand the range on the x-axis. The good thing to know is that the standard deviation is, or 3 standard deviations, 2.12 or something to that nature, and it's 2.1 over, negative 2.1 over here. And you could see that we've got about 99% of the area under the curve. And that's what we have, 99, I think we calculated 99.7. So I can adjust this here. And I think this is 95.5, and anyway, and 68.4 for a standard deviation, which is about here, about 0.707, and minus 0.707. And you can see here for the blue curve, the x-axis is just under this blue, the flattened out part of the curve on the blue model. You could see that we have about 68% of the area covered under the curve, and that's exactly what the Gaussian does. So we have, interestingly enough, we have very precise models for that. Even though we're not able to explicitly solve the integral. So I thought that was an interesting exercise to go through, especially given the fact that they, Boyce and DePrima, gave this as a problem. I don't know, maybe this was the reason why they gave the problem early in the book, so that later on you could see that there was indeed a solution. I like to show that there is a way around, and what seems to be an intractable problem for us. Now, the other aspects that we're going to look at in this this portion of the video are the 4 curves. Remember, there were 4 equations that the assignment was to plot several curves for the functions, because when you solve an integral in general form, you have a constant which yields a family of curves, and so whatever the value c takes, the curve is going to change. at least somewhat. And some of these curves change pretty drastically, especially where there's a discontinuity. The first curve that we were given was the solution to the differential equation that yielded 1 over x plus c over x squared. And that is here in this table. I have my x range right there. You can see I went from minus 10 to 10 on the x-axis. That's our x-axis where we plotted. This is our value of c. So I could have gone with more families of curves, but I thought 7 would be fine. 3 from the negative side of 0 and 3 on the positive side of 0 and 0 itself. And when we look at the plot, I think Excel gives you a nice way, instead of trying to hand plot it back. When this book was written, Boyce de Prima was written, we didn't have the nice graphical tools that we have today, like Excel. We had to plot these things out by hand, and so it was a pretty tedious exercise. But Excel simplifies that quite a bit. And this is the result for that plot with the outer curves right here representing, you see this, where the little dots are the points for the plot when c equals 3. And then we have c equals 2, c equals 1, and then c equals 0. Okay? And they kind of look like hyperbolic functions, the way the hyperbolic function plots. And then we have minus 3 here. And you can see that that's everything remains in the negative side of the y axis, y equals 0. We have the same for this minus 2, c minus 2, and c minus 1. But they all go to either positive infinity or negative infinity as they approach 0. This is one of those functions that is discontinuous at 0 because you can't have division by 0. So now we have the second function, which the solution was x squared plus cx. That was the solution to our differential equation. And again, I plotted for a family of c's between minus 3 and plus 3. And the plot, as you would guess, is a sort of, it's a parabolic because of the second order of the equation, x squared plus cx. So we have parabolas, and they all pass through 0 because we don't have any constant terms in the equation. And the curvature of the parabola is offset by the constant. So our minimum for c equals 3 is on the negative side of the x-axis, right over here, down in that point somewhere. For the curve c equals 2, 1, you can see how the minimum of the curve is shifting. When you get 0, you got a perfect parabola. and then centered on 0, with the minimum centered on 0. -1 shifts to the right of x equals 0, and -3, c equals -3, shifts the minimum of the parabola to the further to the right of x equals 0. So that's what that looks like. And now we're looking at the one of our solutions here for, look at that. I wonder what happened. This is the second chart, third chart. Huh. Okay, yes. Now, the reason I got numbers here, 2 to the x raised to the 3 halves. Because we have a square root, we can't have the square root of negative numbers. The only way we can make this plot is if we put this on the complex plane, and I didn't do that. We could do that if we wanted to, plot this on the complex coordinate system, but I didn't do it in this particular case. I just plotted really only the real portion of the solution, which is 0 and any positive number. So, and I think the book said that we are to look at the equation for x is greater than 0. So that was our domain. And so looking at the plot and the different curves for the plot, we're looking at the positive domain. We're not looking at the complex axis system. So you can see here the impact that changing the constant by one whole number has on that particular function, 2 times x to the 3 halves plus cx. And it's what you would expect for these types of things. Now, this one is interesting. This, I didn't write the function out, but actually this here, here's the function. Y equals the sine of x plus c, all divided by x. Okay, and in this case, rather than, the x-axis has to be angular. So the argument of x, the argument x, has to be expressed either in rads or in degrees. And so I converted the degrees into rads, and which is an easy conversion. You just multiply the degrees by pi and divide it by 180. And you have the rads, and then that becomes the argument of your sine function. So I plotted the function between minus 3.14 or minus 180 degrees. For the different functions that I plotted between, let's take a look. I plotted between minus 10 and positive 10, given a half, 1/2 of an interval. Okay, so each point that I plotted was 1/2 of an interval on the x-axis. And so that led to, I think, 42 divisions on the whole cycle, 43. And so I just multiplied the cycle 180 minus 180 degrees to 180 degrees. That's a 360 degree cycle, one full cycle, by 43 intervals, and then plotted them, and it gave and yielded these. Here's the table. You could see minus 180 degrees to 180 degrees, and I plotted it by, I think it's 8 degrees, a little more than 8 degrees each interval. 8.57 degrees divisions. And then I plotted this function where the argument x is really an angular argument, and I used an integer for c and got the different curves. So that is for 3. The darker blue is for c equals 3. This is c equals 2, c equals 1, c equals 0. And you can see it's discontinuous at x equals 0. Now think about it. It's positive on both sides of 0. And so as you approach 0 from the left or from the right, it's going to go to positive infinity. So these, I didn't plot it there very well, but these here, if we put in symbols, shapes, you would see that this curve would go up, and it's not going to be straight like that. It's going to be somewhat beveled, so not beveled, but it's going to be curved like you see here, except more sharply. So it's going to go, but it's going to be a curve. It's not going to be an angle, sharp angle. And it's going to go to positive infinity. And the same on this side. It's going to positive infinity because the function is positive. See over here, when you have angles from the negative side, you're going to have a sine of the angle is a negative number, and so it's going to give you negative numbers. You're going to go to negative infinity as you approach the discontinuity, and then on the right side of 0, you're going to have positive numbers. So again, it looks a bit like hyperbolic curves, but you have that interesting aspect here, where you got a discontinuous break when you have c equals 0, and now that actually, I'm gonna see if I can cut that. Yeah, I'm gonna cut that. This is really basically the sine function, but the fact that you divide it by x changes the form of the the curve. So you don't end up with a sine curve. In fact, none of it is, in this particular case, none of it is negative. It's always positive, because when you think about it, if the sine of an angle is negative and you're dividing it by a negative x, it's going to be positive. So you're going to have a symmetry on either side of the x-axis. And again, you're going to have a discontinuity at x equals 0 because you can't have anything divided by 0. So you got that break there. And if you can imagine, like I said, it making a sharp bend up to infinity, that's what that curve would look like. So I didn't go to the trouble to plot it because I could probably represent it, but it would be a lot. I'm just telling you here that at this point, this is going to make a bit of a curve. It's going to be a sharp curve, and it's going to go up to infinity from both sides of x equals 0. And that's it for the 4 problems that we were given to as an exercise to plot, so that we could have an idea of how the constant c in the general form of the answer impacts the answer. In other words, the initial conditions can result in significantly different characteristics and behavior of the curves. And so I think it was well worth the exercise. So that ends our video here. We have many more differential equations to solve. We're going to have more first order differential equations, some of them pretty interesting. I noticed that the Bernoulli equation is in here. And then we're going to be talking about how to solve second order equations. That's where we have y double prime instead of just y prime. And looking at general solutions for that. And in mechanics, there are quite a few problems that are involved with differential equations of that type, second order differential equations. There's one where we're going to deal with Laplace transforms, so that should be interesting. So anyway, this is the introductory portion. We're still not done with first order equations. It's a lengthy chapter in the Boyce and DePrima text that I'm using. Again, that was my text from my undergraduate studies in physics, and it's a 40-year-old book, and it just began touching on chaos theory. So we're going to take a look a little bit at nonlinear equations in this book. Nonlinear chaos is a very, very fascinating subject. So with that, I think we'll end this particular video, and I wish you all well.